Good morning. All right, we're going to pick up where we left off in 3.4 and finish that section up today. Again, don't forget the homework on the 3.3 and 3.4 stuff is due by midnight tonight. So hopefully you've at least been working on that. And make sure you get that done by tonight. And then once you're done with that, obviously you can get started on the next section of stuff. We will jump back to section 1.6 from chapter 1 because there's a section we have to do there before we can move on to the 3.6 stuff later on. So just know that we're going to be working on kind of bouncing back and forth between chapter 1 and chapter 3 for the rest of this unit. Again, the goal is to finish this up hopefully by the end of next week. So be expecting that test on chapter 3 to be posted probably Wednesday of next week is what I'm aiming for right now, so that we can get that in by the end of next week. Okay. Any questions, comments, concerns now before we get started today? All right, so let's take a look here at example 3. Okay, so we want to find all the zeros of this polynomial, and then it says sketch the graph, right? So we're going to try to sketch the graph based off of everything that we know up to this point. So what would we do first if we're looking for the zeros of this polynomial? What's the first thing we have to find? Think back to those first two examples we did in this section. What did we do first to find those zeros? Okay, good. So we look at the factors of our constant term first, right? That's going to give us our list of p-values. So what would be the factors of that constant this time? Good, right? So we have 1 and 10 or 2 and 5, right? And don't forget that we always need a plus or minus with all of those factors. It's going to be plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. Those are all the factors of the constant term. Okay? Any questions about finding the p-values this time? All right, once we have that list, now we look at what? Leading coefficient. Good. Our leading coefficient this time is an understood 1. Okay, so what are the q values going to be this time? All right, Haley, let me get this list and then I'll talk about both of them. Good. It's just going to be plus or minus 1, right, because those are the only factors of 1. So again, for the p's, what I'm looking at is this term down here, just the constant. And I'm thinking about what are all the factors of 10, right? Well, I could do 1 times 10, that would give me 10. Or I could do 2 times 5, that would also give me 10. Those are the only options. But I could do like a -1 and a -10, or a -2 and a -5 to get a positive 10. So I have to remember that all of these are going to be plus or minus, because some combination of positives and negatives could give me that positive 10 at the end there. Does that answer your question, Haley? Okay. And then for the leading coefficient, for the q values, we just look at the 1. Only factors there are 1 and 1. So it's either +1, +1, or -1, -1. That's why you have to have plus or minus 1. Now, once we have the p's and q's, what do we have to do with them? Divide. Good. So I'm taking all the p values and dividing by all the q values. Well, in this case, we really only have 1 as the q, right? So we're dividing all those p's by 1. So that's still going to give us 1 over 1 is 1, 2 over 1 is 2, 5 over 1 is 5, and 10 over 1 is 10. And again, all those are going to be plus or minus now. And just keep in mind, if I had a longer list of q values, then I'd have to make sure to divide all the p's by that value also. Any questions about how we got P over Q now? Okay, now remember, this is our list of possible rational zeros. What are we going to do with that list of possible rational zeros now? Good, we're going to test them using synthetic division. Now, rather than having to go through an entire list of, there's 8 here, right, that we would need to test, what could I do to figure out which ones I might want to test? Graphic. That's what I'm going to do next, is I'm going to switch over to Desmos. We're going to look at this graph just to give us an idea of which ones we would actually want to test. So, all right, so we've got x to the 4th minus 5x minus 5x squared plus 23 and plus 10. Okay. If we look at that graph now, what zeros do we think we might want to test this time? All right, so -2 looks like it might work, right? So we'll try that one. It looks like +5, good, might work. And in this case, right, we've got something that's less than 0 and then something that's a little bigger than 2. Do either one of those look like values from our list of possible rational zeros? They don't, right? And so in this case, the only ones that look like they work from our list are the -2 and the +5, right? So I'm going to start with those. We'll see where we get with those two, and then we'll go from there. All right, so I'm going to test -2, +5. So, all right, so if we do -2, again, we're doing synthetic division now. I need all of my coefficients here from the original polynomial. So that's going to be 1, -5, -5, 23, and 10. Okay, so no missing terms this time. So I don't have to fill in any zeros. What's our first step with synthetic division? Bring down the 1. Good. So bring that down. Now we're going to do what? Multiply. Good. 1 times -2. I'm just going to go ahead and do this. -2. Then we remember we're adding, so it's going to be -5 plus -2. That should give us a -7. -7 times -2 should be 14. -5 plus 14, so +9. 9 times -2 is -18. 23 plus a -18 is going to give us 5. 5 times -2 is -10. And then 10 plus -10 gives us a remainder of 0. All right, so what does that tell us about -2 then? It works, right? That is one of our zeros. So now if I'm listing out, I'm going to do it down here, listing out my zeros that work, -2 definitely works. All right, now we want to test the 5. Now, rather than going back to the original list, since I know that -2 worked, what I have left there is okay. I'm just going to keep going with the 5. So I'm going to put 5 here. I'm going to base this one off of those coefficients instead. All right, so my first step is still the same. I'm going to bring down the 1. Now we're going to multiply. 1 times 5 gives us 5. Now we're adding. -7 plus 5 is -2. Negative 2 times 5 is negative 10. 9 plus negative 10 is negative 1. Negative 1 times 5 is negative 5. And then 5 plus negative 5 is 0. And so again, what does that tell us now? Good. 5 is a 0, right? So in my list of zeros, I can put 5. So both of these work. Now, let's think about the factored form of this thing at this point, right? So if negative 2 works, what's one of my factors of this polynomial? X plus 2. Good. So I know one of my factors is x plus 2. What's another factor going to be here? X minus 5. Good. Now, what I want to think about is this line down here and what it actually represents at this point. So if I started with x to the 4th, and I've done my synthetic division twice now, what's the exponent on my x going to be for that line at the bottom? X squared. Good, right? So remember, every time you do synthetic division, you're dividing out an x. And so now we're down to x squared. So this is going to be x squared minus 2x minus 1. That's what that line represents. Any questions up to that point? Now, the question is, can we factor that, right? So if we look at the x squared minus 2x minus 1, can we factor that polynomial? We can't, right? It kind of looks like it might, but in this case, to get the negative 1, we need a positive 1 and a negative 1. That's not going to give us a negative 2x in the middle, right? So we can't factor it. So we're going to have to use quadratic formula at this point to find those last two zeros. So I know that negative 2 and 5 are two of my zeros. Now I'm going to do quadratic formula on this thing to figure out the other two zeros. Well, if I do that, that's going to be negative b, so negative negative 2, plus or minus the square root of b squared, negative 2 squared, minus 4 times a times c, so that's 4 times 1 times negative 1, all over 2a. All right, now we need to simplify that. So remember, a negative negative 2, that's going to become positive. What's negative 2 squared? Good, so that's positive 4. And then we have a minus 4 times 1 times negative 1. That's going to give us what? Positive 4 plus 4. And then 2 times 1 on the bottom is just 2. Okay, so now if I simplify this and add those 4's together, so we have 2 plus or minus the square root of 8 over 2. Can we simplify the square root of 8? Good, right? So the factors of 8 here would be 4 and 2. So if I do that, that's 2 plus or minus the square root of 4 times 2. Square root of 4 is 2, so I can bring that out. So that's 2 plus or minus 2 square root of 2 all over 2. Now, because everything here is divisible by 2, I can actually divide each one of those terms by the 2. And so this is going to give us 1 plus or minus the square root of 2. So 2 divided by 2 is 1. 2 square root of 2 divided by 2. The 2's cancel out and give us square root of 2. So that's what I'm going to get there. So what are those zeros now? What would one of those zeros be? Good. 1 plus the square root of 2 is one of the zeros. And that means the other one then is going to be 1 minus the square root of 2. So that would be my list of zeros. Now, if you wanted to, right, you could get a decimal value for each one of those just to kind of go back to Desmos now and check to see. But if you do that, you would notice that those values, the one that was slightly less than 0 is the 1 minus square root of 2, and the one that was slightly greater than 2 is that 1 plus the square root of 2. And that's why we couldn't test them using our synthetic division, because they're not rational zeros, right? Those are both irrational numbers. Okay, but those are the other two zeros, but the only way to get them is using quadratic formula now. Any questions on that one? And I'm not going to do the sketching the graph piece, right? We have Desmos. We kind of already looked at it, but you would know in this case, x to the fourth, in behavior goes in the same direction, going up because it's positive. And you could plot all those zeros to actually get the shape of that graph. So why couldn't I just divide by 2 before? Where are you asking Haley about, like, at this step right in here? Why couldn't I just divide those 2's? So we have to wait, because there's still addition and subtraction in the numerator. We have to wait until that's completely simplified, because every term would have to be divisible by 2 to be able to divide by the 2. Okay, so it's only because I have a 2 here and a 2 here that I can actually divide by the 2. If that second 2 wasn't there, then I wouldn't be able to simplify that. Does that make sense? Okay. It's because of that plus or minus, right, that both terms have to be divisible by 2 to be able to divide. Any other questions there? So that's going to be our general strategy here, is to find all the rational zeros, do our synthetic division, hopefully get it something down. It looks like this, right, where it's quadratic, because then even if it doesn't factor, then we could use quadratic formula to find those last 2 zeros. Okay. All right, now Descartes' rule of signs. So we're going to let P be a polynomial, real coefficients, just like the ones we've been looking at. The number of positive real zeros of that polynomial is either equal to the number of variations in sign in that polynomial, or is less than that by an even whole number. Now, what this means is that we're going to take our polynomial, we're going to count up how many times the signs change throughout the polynomial, right? How many times do they go from positive to negative or negative to positive? Once we know that, that tells us how many real zeros we could, how many positive real zeros we could have. Now, let's say we count them up and we get like 5 as our sign changes, right? It changes signs 5 times. What this says is that it could be that number or less than that by an even whole number. Well, an even whole number would be multiples of 2, right? So I could have 5 or 3 or 1. Okay, so it doesn't tell me exactly how many positive real zeros I have. It just tells me I could have 5 of them, I could have 3 of them, or I could have 1 of them if I had 5 sign changes. Okay. Now, part 2 says the number of negative real zeros is either equal to the number of variations in sign in P of negative x, or is less than that by an even whole number. So what we're going to do first is plug in negative x into our polynomial. We're going to simplify it. Then we're going to count up how many sign changes we have. And again, it's going to be either that number or less than that by an even whole number. So let's say I count them up and I get 4 sign changes. Well, that means there's either 4 or 2 or possibly even 0 negatives. Okay. You're just always subtracting 2 from whatever number you get. That gives you the options for the number of, in this case, positive real zeros for P of x and negative real zeros if we do P of negative x. Now, you might be asking, well, why is this even useful? Okay, the reason is, let's say I've got a list of possible rational zeros that's, 24 numbers. Well, I don't want to test 24 numbers, obviously. So if I know how many positives and negatives I should have, then at least once I find that many positives or negatives, I know there's no point in testing any more positives or any more negatives, right? I can just test the opposite once I actually have the full list of what I know should be positive or negative. Now, if you've got Desmos or a graphing calculator, you're probably going to be looking at the graph to figure out which ones to test anyway. So this isn't going to be as useful. This is more for if you don't have access to a graphing device and you're just trying to find all the rational zeros. This is useful so that you don't have to test a full list, okay? All right, so let's actually look at how this works. So here's my polynomial. We're going to use Descartes' rule of signs to determine the possible number of positive real zeros and negative real zeros. So first thing we're going to do is we're going to count up how many times does the sign change in this polynomial. Well, if I go through here, I start with a positive value, right? 3x to the 6th is positive. If I go from there to the next term, it's still positive. I haven't changed signs. Then when I go to the next term, it's still positive. I haven't changed signs. The first time I ever change signs is where I go from this positive to this negative right here. So there's one sign change. And then from the negative x to the negative 3, it's still negative. It didn't change signs. So there, in this case, is only one sign change. So I would say the number of positive real zeros is 1. And keep in mind, it's or less than that by an even whole number, but I can't subtract 2 from 1 without getting into the negatives, and so this would only be 1. That's my only option for the number of positive real zeros. Any questions about how I got that looking at that polynomial now? Okay, now to find the number of negative real zeros, now I'm going to substitute negative x in here, simplify it, and then we're going to count up the sign changes. We'll do p of negative x. It's going to be 3 times negative x to the 6th plus 4 times negative x to the 5th plus 3 times negative x cubed minus negative x minus 3. All right, so this first term here, when I do negative x to the 6th power, is that going to be positive or negative? It's going to be a positive, right? Because I'm raising to an even power. So this is just 3x to the 6th. My next term now, I've got a negative x to the 5th power. So is that going to be positive or negative? That one's going to be negative now, so this becomes minus 4x to the 5th. What about the next term, the 3 times negative x to the 3rd? Positive or negative? That one's going to be negative also because it's negative x to an odd power. So we have minus 3x to the 3rd. Then we have minus a negative x. Is that going to be positive or negative? That's going to become positive, so plus x. And then we have our minus 3 down here at the end. Any questions about how I got p of negative x here? All right, now we count up the sign changes for p of negative x. So we start here, we have a positive, right? That's the first term. Now, right off the bat, I go to a negative. So there's one sign change just from the first term to the second term. Then my next term is still negative, so it did not change signs. But then from the negative 3x to the third to the positive x, it changes signs again. There's a second sign change. And then finally, from the positive x to the negative 3, that changes signs again. So I have a third sign change. Any questions about how I got 3 sign changes for p of negative x now? Right, now, based off of that, how many negative real zeros could I have? Could have 3. Is there any other option? You could also have 1, right? So because there's 3 sign changes, we know there could be 3 negative real zeros or less than that by an even whole number. So I have to subtract 2. That's going to give us 1. I can't subtract 2 again, so those are the only 2 options. So I know this polynomial now is going to have at most 1 positive real zero. And in terms of negative real zeros, it could have either 1 negative real zero or 3 negative real zeros. And again, we know in this case, right, if we were to do our p's over q's, right, we'd have plus or minus 1, plus or minus 3 for both. Then you have to do all that division. You're going to get several options. So rather than having to test all of them, right, if I find the one positive that works, then I can just work on the negatives. Right? Or if I find all 3 negatives, then I know that the other one has to be positive. There's no point in checking negatives anymore. Okay? Any questions on using Descartes' rule of signs now? All right. Now, upper and lower bounds. Okay, so we're going to let p be that same polynomial we've been looking at, right? If we divide p of x by x minus b, where b is bigger than 0, using synthetic division, and the row that contains the quotient and remainder has no negative entry. Okay, so whatever we get after we do our synthetic division, that row of coefficients, and there's no negative entries there, then b has to be an upper bound for the real zeros of p, meaning that none of our zeros are going to be bigger than whatever value we just tested. Again, the reason this is useful is if you choose a value and you test it and you get a list of just all non-negative entries along that last line, then we can say, well, none of them can be bigger than that. There's no point in testing any values bigger than what we just tested. Okay? Now, if we do that same thing, okay, in this case, a is less than 0 using synthetic division, and the row at the bottom there has entries that are alternately positive, non-negative and non-positive, okay? And what we mean by that is a non-positive value would either be 0 or negative, and a non-negative entry would either be 0 or positive. And that's why we have to call it non-negative, non-positive, because 0 could be an option there, and it could be counted either way, right? Because 0 is not positive, and it's also not negative. Okay. If that's the case, if it alternates between non-positive and non-negative, then we would say that it's a lower bound, meaning that there's no other zeros any less than that value that we just tested. Again, that's a good way to kind of eliminate part of your list if you have a really long list of possibilities, is once you see that something is either an upper bound or a lower bound, you can start cutting off values and not have to test them at all. Okay, so let's look at how this actually works now. So we want to show that all the zeros of this polynomial are somewhere between -3 and +2. So what that means then is we don't want any values less than -3, and we don't want any zeros bigger than +2. So we want -3 to be a lower bound, and we want 2 to be an upper bound. So if we can show that, then we know that all of our zeros have to be between -3 and +2. All right, which one do you want to show first? -3 or +2? All right, let's go with the -3. So I'm going to put -3 in here, and we're going to do our synthetic division. Okay, so we got x to the 4th minus 3x squared plus 2x minus 5. I'm missing the x cubed term, so don't forget we have to put a 0 there. It's going to be 1, 0, -3, 2, -5. All right, first step is synthetic division. Bring down the 1. Now we multiply. 1 times -3 is -3. Then we add. 0 plus -3 is -3. -3 times -3 is +9. -3 plus 9 is 6. 6 times -3 is -18. 2 plus -18 is -16. -16 times 3 is 48. And -5 plus 48 is 43. Now, obviously, -3 is not a 0, right? But we need to see if it's a lower bound. So what should happen here if -3 is a lower bound? So we said right here, we can show that it's a lower bound if we are alternating between non-positive and non-negative numbers along that last line. So if we look here now, is 1 a non-positive or non-negative number? It is not negative, right? So it's non-negative. So we would say we have a non-negative here. Is -3 non-positive or non-negative? You create NP or NN. It's NP, right? This is non-positive. 6 then would be a non-negative. -16 is non-positive, and 43 is non-negative. Because it alternates between non-negative and non-positive all the way down, we can say then that -3 is a lower bound. Again, the reason we have to classify these as non-negative, non-positive, because if we get zeros there, and you'll see this, we're going to do one in the next example, then it could actually, 0 can be counted either way. Okay, and so we have to be careful there that we classify them not as positives and negatives, but as non-positives and non-negatives. Any questions about -3 being a lower bound now? All right, now let's see if we can show that 2 is an upper bound. So steps are still the same. We're going to list out the coefficients. We're going to do our synthetic division. We have 1, 0, -3, 2, and -5. We're going to bring down the 1. Multiply here. 1 times 2 is 2. 0 plus 2 is 2. 2 times 2 is 4. -3 plus 4 is 1. 1 times 2 is 2. 2 plus 2 is 4. 4 times 2 is 8. And -5 plus 8 is 3. Now, what do we want to end up with on that line if 2 is an upper bound? That's right, no negatives, right? So all non-negative entries. Well, if I look down my list here, 1 is non-negative, 2 is also non-negative, 1 is non-negative, 4 is non-negative, and 3 is non-negative. Therefore, we can say that 2 is an upper bound. And because -3 is a lower bound, 2 is an upper bound, that means that all of our zeros then have to be between -3 and +2. Again, if you look at your polynomial here, 5 would be one of the factors of that constant, meaning that plus and minus 5 would be options. Once I know that -3 and +2 are upper and lower bounds, I know that 5 and -5 don't work, so then I can narrow my list down and only test values then that are somewhere between -3 and +2 instead. Okay. Any questions on lower and upper bounds there? All right, let's take a look at this one. So this time we just want to show that all of our zeros of this polynomial are greater than or equal to -4. Okay, so in other words, we're trying to show that -4 is a what? Lower bound. Good. We want everything to be bigger than this. So we want to show that this is a lower bound. So we're going to do our synthetic division here. -4. Coefficients, I'm not missing any terms this time, so I just have 1, 4, 3, 7, -5. Bring down the 1. So this time we have 1 times -4 is -4. 4 plus -4 is 0. 0 times -4 is 0. 3 plus 0, 3. 3 times -4, -12. 7 plus -12, -5. -5 times -4 is 20. And -5 plus 20 is 15. Now remember, if we have a lower bound, we need these things to alternate non-positive, non-negative, right? So let's start with the 1. Is that going to be non-positive or non-negative? That one's non-negative, right? So we have a non-negative entry here. We need this to alternate, right? If we're trying to show this is a lower bound. 0 could go either way, but what are we going to call 0 this time so that it alternates? Non-positive, right? Again, whenever you have a 0, you get to choose whether it's non-positive or non-negative. We want to show this is a lower bound, so we're going to call it non-positive. All right, now 3 is going to be what? Non-negative. -5 would be non-positive. And finally, 15 is non-negative. And because we have alternating non-positives and non-negatives all the way down, we can say that -4 is a lower bound. Okay. Again, meaning that all of our zeros this time have to be greater than -4. Any questions on that one now? All right, example 7. So now we want to factor completely this polynomial. All right, so first step, we're going to find all of our P's and Q's like we did earlier. Then we're going to test to see which ones work, and then we'll go from there to see if we can find all the factors of this polynomial. So if we start with P's, what are going to be the values of P this time? Okay, so we're going to have 1 and 3. Anything else? Remember, we're looking at the constant term here for the p-values. Nine, right? So don't forget that 9 is still a factor of 9. So you have plus or minus 1, plus or minus 3, plus or minus 9. Those will be our factors of 9. Now let's look at the Q's. Remember, now we're looking at our leading coefficient. So what are going to be the factors this time? That's the 1 and 2, right? So we have plus or minus 1 and plus or minus 2. Now we have to divide. So we do P over Q. Remember, that means I'm dividing every P value by every Q value. So I'm just going to start with all the P's and divide them by the 1. So that's going to give us plus or minus 1, plus or minus 3, plus or minus 9. Then we need to divide all of them by the 2. So we'll get plus or minus 1 over 2, which is 1/2, plus or minus 3 over 2, which is 3/2, and plus or minus 9 over 2, which is 9/2. Any questions about how I got that list of P over Q's? Okay, what do we want to do next? Good. Let's graph to see which ones might work, right, before we actually test anything. I'll switch over to Desmos. We'll put this in there. Take a look at the graph. All right, so we got 2x to the 5th plus 5x to the 4th minus 8x to the 3rd minus 14x squared plus 6x plus 9. All right. So looking at our graph now, what values do we think we want to test this time? A -1 looks like it works. Good. What else? A +1 looks like it works. Good. Looks like -3. Good. And yeah, somewhere between 1 and 2, right? So 1.5 would be 3/2, and that was one of our options. So we can test that one. Okay. Now, is there anything else you notice here just looking at the graph? Yeah, it looks like -1 bounces, right? And so we know that it might have an even multiplicity, so it might happen multiple times. So just keep that in mind as we're testing now. But I'm going to go with just this list of -1, +1, -3, and 3/2, right? We'll test those, see where we get, but keep in mind that the -1 could potentially happen an even number of times, okay? All right, so let's test these now. All right, so I'm going to start and go in order here. We'll go with the -1 first. We got -1. List out your coefficients. Again, I'm not missing any terms this time, so it's going to be 2, 5, -8, -14, 6, and 9. Bring down your 2. Then we multiply. 2 times -1 is -2. 5 plus -2 is 3. 3 times -1 is -3. -8 plus -3 is -11. -11 times -1 becomes +11. -14 plus 11 is -3. -3 times -1 is a +3. 6 plus 3 is 9. And 9 times -1 is -9. And so we do get a remainder of 0 here. Right, so now I know that -1 does indeed work. And so in terms of my list of zeros here, -1 is good. All right, now remember, at that point, we can just continue on from that line. We don't have to go back to the original coefficients. So I'm going to test the +1 next. So I'm just going to put 1 over here. Bring down the 2. And we multiply. 2 times 1 is 2. 3 plus 2 is 5. 5 times 1 is 5. -11 plus 5 is -6. -6 times 1 is -6. -3 plus -6 is -9. And -9 times 1 is -9. We get a remainder of 0 again. It tells us 1 works. So I can add that to my list of zeros. Any questions up to that point? All right, now I'm going to go ahead and test the -3 next. And just continuing on from this line here. Bring down the 2. 2 times -3 is -6. 5 plus -6 is -1. -1 times -3 is +3. -6 plus 3 is -3. -3 times -3 is +9. And -9 plus 9 is 0. So -3 works. It's another 0. Now, what I would suggest at this point is we know we started with x to the 5th power. We've divided out 3 x's now. So what are we down to for this line at the bottom? X squared, right? Okay, so we started with x to the 5th. We've divided out an x 3 times. We're down to x squared. So I know my factored form up to this point. We're going to have an x plus 1 for the -1, an x minus 1 for the 1, and an x plus 3 for the -3. And then this line here is going to be 2x squared minus x minus 3. So instead of continuing and doing the 3/2 next, which you could do, right? I'm just going to look at this now and see if it factors, because if it does, that'll give me the remaining zeros anyway. Well, can I factor 2x squared minus x minus 3? Okay, so just for the sake of time, I'm going to go ahead and do this. So this is going to give us a 2x, an x, then we need a 3 and a 1. The 3 is actually going to have to go here and the 1 over here so that I end up with a 2x on the outside, a 3x on the inside. I'm going to need the 3x to be the negative to give us a negative x in the middle, which means that's a positive 1 down there. So that would be our completely factored form. Notice here that we actually have an x plus 1 factor that happens twice. So I could actually write that as x plus 1 squared times x minus 1 times x plus 3 times 2x minus 3. This 2x minus 3 would give us the 3 over 2. And because that x plus 1 happens twice, we know that negative 1 now is going to have a multiplicity of 2, and that's why it looked like it bounced on the graph there. Okay, so this would be the factored form. That's all we were asked to do is factor, right? So this would be our answer right here. Okay. All right, so we'll stop there for today because I know we're at time. I will hang out for a couple more minutes if you've got any questions about this. Don't forget the homework on 3.3, 3.4 is due by midnight tonight, so make sure you get that done. Let me know if you've got any questions. Have a great afternoon, and I will see you all Wednesday.